Johnny is a consultant for Involved since 2014, which is 6 years, focusing on .NET architecture and backend development. Prior to joining the Involved, he has had experience developing software for Carlos since 2008. So that's a long time. Come on, that was a long time ago. And for all I know, he has been passionate about .NET ever since it was released. So yeah, his areas of expertise are so wide, you can ask him basically any questions you want. What questions would you like most, Johnny? About what?
About traveling and theme parks.
Traveling and theme parks. Okay, let's see. I can answer those questions too.
Nice.
Since 2010, Johnny is spending most of his free time teaching, and when he's not working or teaching, he likes some casual gaming, which I do like too, so we have something to talk about. Scuba diving, learning to play the piano, and traveling the world, as he said, and visiting as many theme parks as possible. So that's all the information about Johnny, and stage is yours, I think.
All right, thank you. So I'm very excited to be talking on Build Stuff this year, the Rock Code edition. Very nice. So I'm going to talk about quantum computing today. And just like a very good rock concert, I hope that everyone will enjoy this. Maybe will learn something and probably also be a little bit confused. And if it was a good rock concert, maybe you will have some nosebleeds also. We'll see. A little bit more about myself. So as you heard already, my name is Johnny. I'm a little active on Twitter, so you can always follow me on Twitter. If you have any questions after the conference, you can also ask me on Twitter. I have a GitHub page, and on this GitHub page, I have my personal projects, and I also have all of my conference presentations. So after the presentation, you will find all of the resources right on my GitHub page. And I will share a link at the end of the presentation. I work for Involved IT, which is a consultancy firm in Belgium, and I'm actually a software developer / architect working for Involved. And this is basically .NET and C# related. So what the hell am I talking about quantum computing then? Well, about 2 years ago, I was in the same place as you guys. So I was listening to a conference and it had a presentation on quantum computing. But I think after the presentation was done, I only got about 25% of the content that I really understood. So I decided to do my own talk. From the perspective of a software developer in .NET and C#, trying to make the message more clear to people like me, so people like you, I hope. So my goal today would be to explain quantum computing and the future of quantum computing to you, and hopefully that you will understand more than the 25% that I understood 2 years ago. So it's basically a hobby. I don't do it professionally, but I want to learn as much as I can about it. If you have any questions, next to my Twitter, you can always contact me on my company email address, and that's it. So let's shut up about me and dive right into the quantum computing stuff. So why in God's name would we want quantum computing? Well, today, it's hard to believe, but today we still have a lot of problems that we cannot solve by a classical computer. So when I'm talking about classical computers, I mean the computer that you're using at home, a laptop, a PC, your smartphone, which is all a computer. But there are many problems that cannot be solved by that kind of computers because the CPU in a computer has its physical limits. Maybe you noticed, but the last decade, CPUs didn't really get a lot faster. We were just putting more CPUs in one computer basically, but we are on a limit. The current classical computing architecture does not allow us to scale it even more, to be faster, to be smaller. It becomes very difficult. But the world where we live in is so complex. Like think on about the atomic structure of everything we live in. It's so hard for a classical computer to work with that, and that's why we need something new. And hopefully, quantum computing can help us solve that issue. So I have an example of such a problem that is quite complex for a classical computer, and this is actually a problem that's been described to me by a teacher in elementary school. So I was in class, and he said, okay, if you have a chessboard, there's a kind of a jump you can do on a chessboard using the horse. It can go 8 different directions. But if you start on a random spot on the chessboard and you make a jump, you come right on the next spot, and then you do the same jump over and over and over again until you have visited all of the squares on the chessboard without missing one. So this is a problem you can solve, and I did it on the right-hand side. So the right-hand side is a picture that I drew myself. It took me about 1,000 years to reach that conclusion, and it's actually the same thing with a classical computer. If you write a brute force algorithm, so if you take out your computer, your Visual Studio, C#, whatever, and you start writing an algorithm that visits all of these squares one by one, and if you make a mistake, which means if you're stuck somewhere because you can't do another jump because all of the squares are already visited, you have to backtrack. So you can write this algorithm, and if you do it correct, it will take a few seconds. If you make the wrong decisions by accident in your brute force algorithm, it can take your computer years to find a solution. And that is just crazy. Why does it take years? Your CPU is so fast. That's because there are so many permutations. There's only 64 squares, but there are so many permutations for you to visit in a specific order. So this is a problem that to our minds looks very simple, but to a computer is actually very hard to solve. Another cool example is something even more simple. If you take a regular piece of paper, let's find a piece of paper right here. So this is a regular piece of paper. This has a thickness of about 0.1 millimeter. So 0.1 millimeter. If I fold it double, the thickness of the paper doubles, so 0.2 millimeter. And if I keep doing this 42 times, so 42 is not a large number, 42. It's not physically possible. You can try. I think 7 or 8 times is the maximum you will be able to do because you don't have enough force. But if you do it 42 times, the thickness of this piece of paper will reach from the Earth to the Moon, 500,000 kilometers. This is again mind-blowing. 42 is such a small number. It's so comprehensible. But folding something, so doubling something 42 times, is just a very large number, so 500,000 kilometers. And this is the exact reason why quantum computing is something that is needed, because for classical computers, it's the same thing. A problem can seem very easy, but if you just add one small variable to the problem space can double or exponentially increase, and your computers cannot solve this in 1,000 years. So quantum computing actually uses phenomenon from quantum physics that are experimentally proven already. So it's already 100 years ago that scientists knew that something weird was going on a subatomic level. So on the level of microscopic things like electrons or photons, some weird things are happening. And they can't really explain why those are happening, but they have proven by experiments that they are happening. And two of those phenomena are superposition and entanglement. What is it all about? So superposition first, so on a quantum level, so the very small microscopic objects like electrons, they have specific properties, and those properties can have a specific state. So for example, a spin of an electron, which is the image on the left-hand side, can be up or it can be down. It's not really something tangible. You can't really look at an electron and see it spin. It's something that you can measure with experiments. But we like to talk in physics about a spin of an electron that is in a state up or a state down. And from experiments, we can also see that this spin property can actually be up and down at the same time. And this is what they call superposition. So it's not really up, it's not really down, it's somewhere in between. And when I'm saying something in between or at the same time, that's also not correct. It's actually some kind of probability thing that says, okay, if you are to measure the spin of an electron, there is some percentage is going to be up and some percentage is going to be down. But the electron itself did not yet make the decision. It only makes that decision if you actually look at it, if you measure it, and then it will make that decision based on some probability wave, they call it. So this is very, very difficult for us on a macroscopic level to grasp. It's like you're sitting on a chair, but maybe that chair is not underneath you, maybe it's underneath the person who's sitting next to you. So it's very weird. only works on a microscopic level, so it doesn't work in real life, luckily. There's only one thing I know where it works, and it's a USB key. So if you have a USB key, you want to put it inside of your computer, it's in superposition. You try it one way, it doesn't work. You try it the other way, it doesn't work. You flip it around a couple of times, it still doesn't work. You really have to look at the orientation of your USB slot, and then when you look at it, you measure it, it takes a decision, it's up or down, and then you can safely put it inside. So that's the only thing on a macroscopic level that I know of that actually works in this quantum way, in the superposition way. The second thing is entanglement. So this is even more weird. So if we have an electron, for example, it can be entangled to another electron, which means that if both electrons are in superposition at the same time, so that's the image on the right-hand side, they can be somehow entangled together, which means that they are basically one and the same, but still they're two separate entities. And if you observe one of them, it will make the decision if the spin of the electron is up or down. But weird is that the other entangled electron will make the same decision at the same time. So you look at the left-hand side, the left electron, it decides its spin up, and then the right-hand side electron will decide its spin down. It's always going to be the opposite. And this, scientists really don't know how this works. They tested this on multiple occasions. If they send one entangled electron to a lab at the other side of the world and they observe it, they are still connected, but they are so far apart. They are not communicating. They also tested this. There's no communication between them because communication or not communication goes faster than light because it's instant. So yeah, we really don't know what the hell is going on here. Some scientists think that there's like wormholes in between of those electrons to be able to make them communicate, but basically when scientists talk about wormholes, they are just saying, I have no idea. There is an experiment called the Double-slit Experiment, which is very cool, but I don't have the time to talk about it in much detail today. So during my workshop tomorrow, I will dig a little bit deeper into this. But you can find videos on YouTube that explain this, and this clearly explains superposition and the weird things that are going on a quantum level. So I'm going to skip this for now. This is, for example, also something that you can Google. It's called Quantum Experiment at Space Scale. And this is what the entanglement stuff is all about. So there's actually been an experiment where we are using lasers from a satellite orbiting the Earth, and we're entangling two photons, photon, the elementary particle of light. We're sending one to China, one to Austria, and those scientists really observe one of those two photons, and they can see that both are collapsed. So both have made a decision. One is up, one is down, and they really don't know how it works, but it works. So why the hell do we want to do this crazy stuff with our computers? Well, basically, there's a couple of use cases. For example, security. We hope that we can create algorithms which are much faster than classical algorithms that can break our current security protocols and can create new security protocols for us. So for example, the public-private key encryption in theory can be broken by a very powerful quantum computer, but today we don't yet have a powerful quantum computer, so we cannot break that. But there are things that quantum can deliver us, for example, quantum key distribution, where we can use entangled particles to share passwords or share keys over a quantum internet, for example. Drug development is another one. When I talked before on our world we live in is quantum by nature. Everything is quantum by nature. There's quantum particles inside of you. When we are developing drugs, those drugs need to work inside of your quantum body. So why aren't we using quantum computers to simulate a quantum system? Because that should be a lot easier to do. For a classical computer, it is very, very hard to actually simulate a quantum system because there's too many variables, there's too many interactions between atoms and particles inside of your body to actually 100% simulate what a drug will do. And that's basically why we still do tests on animals, because we can't for sure know what a drug does on a human because we can't simulate it using our classical computers. So for example, gene sequencing and protein folding are these kind of things that you can use software on all of the computers in the world working together, and still it's so slow really find useful things for us. A third example is, for example, machine learning. In machine learning, we must analyze very large quantities of data. We also want fast feedback, so we need fast analyzing to have fast feedback. And if we really want to emulate a human mind, that we're just going to need a lot more power to do that. So again, we hope with quantum computing, we can actually leverage that power from our quantum world. So finally, why we need quantum computers? Maybe the biggest question, and I know that everyone is already asking this question, can it run Crysis? So can my quantum computer run Crysis? Well, the answer is probably yes, but why? So what I want to talk about with this is a quantum computer is just another kind of computer. And quantum computers are never going to replace our classical computers. So your classical computer is very good in doing classical things, like, for example, running Crysis. If you want to play a computer game, you can do that on a classical computer. A quantum computer, that will do very good for very specific problems. And in theory, the kind of architecture that we already have today for quantum computing is compatible with classical computers, meaning that we can run every classical algorithm on a quantum computer, but it's going to be really expensive because a quantum computer is very hard to build. It's very hard to keep running because today it needs to be cooled down to zero, absolute zero temperature, which is very expensive. It's also very volatile, so it's very hard to actually run long-running algorithms. So in theory, it can be done, but in practice, we will not do it, and we will only use quantum computers for very specific problems that they can solve exponentially faster than classical computers. Also, if in the future we're going to do quantum computing, it's, I think, always going to be a classical computer and a quantum computer working together. So you're going to have a classical part of your algorithm that's going to work in conjunction with a quantum part of your algorithm that both will run on classical and a quantum computer side by side. So I'm going to dig a little bit deeper into how this actually works. And then later on in the presentation, I will show you an example in a quantum programming language from Microsoft, which is called Q#. So the first thing you need to know is that quantum computers actually work the same way as classical computers. We are going to represent bits both in classical and in quantum computers. So a bit for a classical computer is just 0 and 1, like everyone knows. And we can combine these bits into bigger numbers. And for example, here we have 1 0 0 1 1 0. On a quantum computer, we're going to do the same thing. We're going to represent the two states 0 and 1. We're going to write it down a little bit different, just so we know that we're talking quantum. So there's going to be like a vertical line in the beginning of the 0 and then a bracket at the end. This will just tell us it's a quantum state 0 and not just a classical state 0. This is actually called the Dirac notation, named after a mathematician called Paul Dirac. He invented this kind of notation for quantum specifically. So the same thing, 0 and 1. 0 in quantum is 0 in classical, 1 in quantum is 1 in classical. We can also combine those qubits into a combined quantum state, and it's again the same thing as classical. So 1 0 0 1 1 0 with the Dirac notation to define that this is a quantum state and not a classical state. So the interesting thing here is that if we talk about superposition, and superposition is the thing that will give the power to quantum computing that we need to be able to specify this kind of probability wave between how much probability do I have to collapse to 0 and how much probability do I have to collapse to 1. So we're going to do this mathematically. So if you want to dig deep into quantum computing, you're going to have to need a little bit of math. You don't have to be afraid of math. The math used in quantum computing looks very difficult, but it's actually quite simple. And I had the experience the past 2 years. I was a bit afraid of math, and today I can say that it really helped me understand everything. So basically, when we talk about a superposition state, we're talking about some alpha value and some beta value, and they will describe the probability of it being 0 or 1. There's also a kind of normalization formula that says that the absolute value of alpha squared plus the absolute value of beta squared should always equal 1, and the 1 actually means that there's always 100% probability that the both probabilities added together will be 100, of course. So then things become complex, literally, because the alpha and the beta values are not just real numbers. It's not just a percentage. It can actually be a complex number. So if you remember from school, complex numbers are numbers that contain a real number, A and C, and they have an imaginary number, B and D, because I squared equals -1 or something. Something you need to know in the back of your head, that when we calculate with quantum, we really have to calculate with complex numbers. That's all that I'm going to say about that. If I do the calculations correctly and I have a perfect superposition state, so my USB key, it can only be upside down or the correct way. So it's 0 or 1. So it's 2 states. If I am in superposition, perfect superposition, 50% up, 50% down, then I actually mathematically have to think about 1 over square root of 2 is my probability, because the formula from before said that alpha squared plus beta squared should equal 1. And 1 over square root of 2 squared is 1 over 2, or half, plus 1 over square root of 2 squared is half. So half plus half. So this really describes, for me, a quantum state that's in perfect superposition, 50% collapsing to 0, 50% collapsing to 1. And now things become interesting. If we do a little bit recap, we see that a classical bit can be 0, a quantum bit can be the same 0, but in the Dirac notation, the same for 1. In superposition, we have those two values, alpha and beta, which describe the probability of those states. Those are also complex numbers to make things more complex, pun intended. Very important that the value is known after measurement. So when you put a qubit in a quantum computer in superposition, you can't look at it. The moment you look at it, it will make the decision if it's 0 or 1 based on the probability. So if we would look at this more graphically, because maybe that's easier to do, you can see here a sphere. And this sphere is actually called a Bloch sphere, and this helps us to map the state of a single qubit in three-dimensional space. So basically, you should think of the state of a qubit as a vector in this space originating in the center of the three axes x, y, and z. So there's a vector from here to somewhere on the surface of the sphere. And on the right-hand side, you can see a vector which is Dirac notation of psi, and psi is just a arbitrary quantum state. So it can be a qubit in superposition. It is a qubit in superposition. And that vector can actually move around the sphere all over the surface, which means that there's a lot of data we can actually store inside of a single qubit, because the alpha and beta value, they only have to adhere to that normalization formula. But those two values can actually be whatever they want. The result of that normalization formula should just be 1, which means there's an infinite amount of possibilities for different kinds of superpositions you can have. So there's a lot of data inside of a single qubit. Just going to skip this one and come back to this later. So if we look at these systems, if we add a single qubit to a quantum state, we're actually going to have 4 values now, because if you look at the classical thing, 1 bit can actually describe 2 numbers, 0 and 1, but 2 bits can describe 4 numbers, 0, 0, 0, 1, 1, 0, 1, 1. And here is now the power of quantum computer, because we can now have 4 states with only 2 qubits. We can have a probability that it's going to collapse to one of those 4 states. And if it's a perfect superposition, each state will have a probability of 25%. But it's still a lot of data that's being stored in those 2 qubits, because we have 4 complex numbers, 4 complex values. And if we add another qubit to that system, now we have 8 complex values. And with each qubit we add to that system, we're actually doubling the amount of state we can store within that system. So basically, when we have an exponentially large problem, it's very hard to solve that on a classical computer, because we can't increase the speed of a classical CPU exponentially. If you have a very powerful CPU and it's made out of 1 billion transistors, if you just add 1 transistor to that architecture, it's going to be slightly faster, but you're almost not going to notice the difference. For a quantum computer, that's very different. If you have a computer, say, let's say 100 qubits, if you want to make that system twice as powerful, you only have to add 1 qubit to that system. And now it's twice as powerful. So this exponentiality will hopefully help us to create really powerful computers, because we just need to add one basic building block for a quantum computer, which is something that can represent a qubit. We only have to add one to double the power of that computer system. So before I go into Q Sharp, or the programming language from Microsoft, I'm going to tell you that lots of these things that we're doing in quantum today are actually very mathematical in nature. Also, when we are writing computer programs in like C# or Java, we're doing this on a really high level. So we're talking almost English to our computer to make us do something. For quantum, which is quite young, we are actually still doing things very basic. So think of quantum as really writing circuits. So if you would write a circuit for a classical computer, it's using gates like AND, OR, NOT. For quantum, it's the same thing. So we're actually using quantum gates. But the issue is, for classical computers, when you think about classical gates, and you think, for example, an AND gate, and you put 2 bits inside of your AND gate, you just, from the top of your head, you can immediately say what the result is going to be. So that's not very hard to do. But for quantum, it's different, because when you have a quantum state that's in superposition, and its probabilities between multiple output states, and then you put that through a quantum gate, it's very hard to do from the top of your head, because there's so many mathematics behind that. That's why this slide actually tells you that there's another way to represent a state in the quantum world, and it's linear algebra, it's matrices. So if you look at the left-hand side, and you can see the Dirac notation for the 0 state, on the bottom you can see a matrix that represents the 0 state, and on the right-hand side you can see a matrix that represents the 1 state. And thanks to these matrices, we can actually use a piece of paper or some software on your PC that can do mathematical calculations. We can calculate the result based on the gates we use for quantum computing. So this is, for example, a gate in a quantum world that is probably the most easy gate for you to comprehend, and it's the gate that flips a bit from 1 to 0 and from 0 to 1. So also in quantum computing, we can have gates that work on a classical level. So if you have a quantum state 0 and you put that state through an X gate, you will actually flip the state around. And you can also see the same thing on the block sphere. So the block sphere, if your qubit state is 0, it's going to be a vector that points upwards the z-axis. And if it's 1, it will point downwards the z-axis. So if you do an X operation, so an X gate, it will just rotate the state of that qubit around the x-axis in the block sphere, and that will flip it from 1 to 0 or from 0 to 1. And if you want to do the calculations, you can use this matrix on the right-hand side to actually multiply this matrix with the state matrix of your qubit. This is an inverse identity matrix, so it will just reverse the 1 and the 0 in the matrix, giving you the other state. So it's very easy to work with if you know a little bit of linear algebra. So there's other gates that you can use. There's the Y gate, it will flip around the Y-axis, and this uses I. So here complex numbers are really involved. Then there's the Z gate, which will flip a qubit around the Z-axis. And then there's more complicated gates. The H gate is the gate that puts a qubit in superposition or gets a qubit out of superposition. So in this block sphere, you can see a vector pointing up will be in state 0. If we put it through the H gate, or Hadamard gate, we will put it in superposition. So it's going to be a rotation around a diagonal axis shared between the Z and the X-axis, and the result will be in front on the positive side of the X-axis. And this is actually superposition. Why? Because a vector is now actually positioned on the plane in between the 0 and the 1 state. And this is perfect superposition, because now we have a 50% chance of that vector collapsing to the 0 state in the top, or 50% collapsing to the 1 state in the bottom. If your vector is located not on this plane, but somewhere above or below, you can see that the probabilities are different. So if the vector is pointed up, there's going to be a higher probability of it collapsing to 0. If the vector is pointed down, there's going to be a higher probability of it collapsing to 1. And this is basically what quantum computing is all about. We are going to have a number of qubits. We're going to put them in superposition or even entangle them together. We're going to force those qubits to be in some kind of superposition with some kind of probability that works in our benefit. And then we're going to do measurements, and hopefully that probability will actually work in our benefit, and the result of our algorithm or circuit will resolve our problems. And this is, of course, something that's very difficult. Here, you really need to have a deep knowledge of how this all works to actually make sense of that and create useful algorithms. So let's do some examples. So first, there's IBM Q Experience. I'm just going to very quickly show this to you because I think this is just very cool if you want to learn about quantum. So IBM built actual quantum computers. So they have running quantum computers, and you can actually use them. So on the right-hand side in my screen, you can see a number of quantum computers, and you can see that they're actually having a queue. So when you submit your algorithm, you have to wait in the queue for that quantum computer to solve your issues. But these quantum computers are not very powerful. They can be used to do learning or investigation, but they only have 5 qubits, as you can see. So if you want to create an algorithm, it's going to be very visually. So you can actually have a visual interface that shows you 3 qubits and then a whole lot of these quantum gates or quantum operations that you can do. So for example, if I drag an Hadamard gate on top of a qubit, the first qubit in the bottom, you will see that we now have 3 bits, 000 and 001, because I only used the top bit. And we have a 50% chance of my bit collapsing to 0 and a 50% chance of it collapsing to 1, because we put it in superposition. If I take it out of superposition again, we now have 100% chance of it collapsing to 0, because it's 0, because we put it in superposition and back out of superposition. So this is how that works. So with this, you can basically drag quantum gates on top of your qubits from left to right, which represents the time of your algorithm. So you will start on the left-hand side, and you can do one operation after the other until you reach your final end result. If you're really doing useful algorithms at the end of your algorithm, you really have to measure your end result, which will then be calculated into a classical 0-bit for this specific case. You can also use multiple qubits. So if I drag this Hadamard gate on top of the second qubit, we now have a 2-qubit system, and both qubits are in superposition, which means I have a 25% chance of them collapsing to 0, 0, 0, 1, 1, 0, and 1, 1. And you can, of course, continue by putting more qubits in superposition to have your probability spread out over more quantum states. So this is very fun to do things with, just to learn about what different things you can do. There's lots of examples of existing algorithms, and you can try to recreate those algorithms using this tool. So I just wanted to show you the visual representation of what a quantum circuit looks like. So I have added this link in my slide so you can actually visit to see the result. So now Microsoft, they did the same thing, but a little less visually. So I'm going to show you Visual Studio Code. So Microsoft has a quantum development kit, which means that they have created their own programming language and the tools for you to use that programming language. You can use that from Visual Studio or Visual Studio Code. It's up to you. It's just if you install the SDK, it will be available in Visual Studio Code and Visual Studio automatically. So if I'm using Visual Studio Code, so I can open my command palette, I can say I want to create a new Q# project. So Q# is the quantum language from Microsoft. It should ask me what kind of Q# application I want to create. I want to create a standalone console application. So a console application actually means that it's going to run in a simulated environment on my own PC, so not on a real quantum computer. And it's going to be a console application that I can run to see my simulated results. You can also do unit testing in quantum the same way as we know in our classical programming languages. And you can create libraries to create NuGet packages so that you can have something in quantum that's is able that other people are able to use in their quantum algorithm. So you can actually create shared quantum libraries with some quantum stuff inside of that. So let's create an empty application. So let's call it Q#. I'm going to open it, and I'm going to show you what Q# looks like. So it's a bit a combination of C# and F# basically. So it's a functional programming language. So you should be quite familiar with the layout. It uses curly braces. It uses operation, which is basically a quantum method, something that you can execute. The entry point attribute will make sure that this is the one that's being run. So this operation will automatically be run like your main method in your console application. This is your usings from C#. So open a namespace to use stuff from that namespace, and we can begin programming. So for example, I want to create a system that uses 1 qubit. So I'm going to do using, just like in C#. When I want to use resources that need to be disposed of later, I can do using. So Q equals a qubit. So I'm going to assign 1 single qubit. Then if you want to put that qubit through a gate, it's just like calling a function. So it's H for the Hadamard gate to put it in superposition on top of my qubit. Now, if I want to measure the result of my qubit, I can use that the measure function for that. So M will do a measurement. So that qubit will collapse with a 50% chance of being 0, 50% chance of being 1. I can store the result in a variable called R. So R equals measurement of Q. And then I need to reset my qubit because Q# really likes a qubit to be reset to its original state. So the original state for a qubit will always be 0. So with this operation, I'm putting it in superposition. I'm doing a measurement on that superposition. I'm resetting the qubit, and I'm going to write the result to the console with some string interpolation like C#. So I'm just going to do the result to the console. If I do view terminal, I can actually now use .NET to run this. So .NET run. This will take some time to compile. And while it's compiling, I can tell you that this can actually be run on a real quantum computer. Microsoft is working on Azure Quantum, and Azure Quantum will make sure that you can basically make a connection from your development environment to Azure Quantum, and you can push your algorithms to Azure Quantum. That will be able to run it on an actual quantum computer, and the result will be sent back to you. But right now, .NET is helping us to create a simulated environment on your local PC. It will simulate in the background how these qubits should interact using a pseudo-random generator, and it has now generated 1 as a result. So if I do it again, it should generate still 1, but it should actually be a 50% chance of being 1 and 0. So now we have 0. I'm going to do one modification just to show you the power of Q#, and then you can see some more syntax. So let's say I will do this 100 times. So from 0 to 100, it's a for loop. So I'm going to do whatever is inside the for loop 100 times, like this. I'm going to declare a variable result, which equals 0. I'm going to print out that result in total. And then when I do the actual measurement, let's say that I'm going to set the result to plus equals R. So R is going to be 0 or 1. So I'm just going to add that number to my result. And then if I do it 100 times, result will be around 50, because sometimes it's 0, sometimes it's 1. It's 50% chance. So my result should be around 50 because I did it 100 times. But R is actually not a number, so I have to do some conversion. So if R equals 1, then I'm going to add 1 to that result. Otherwise, I'm going to add 0 to that result. And so I will do another .NET run, and this should actually give us a number around 50. So while that is loading, I'm going to go back to my slides. I'm going to talk a little bit about Azure Quantum, and then I'm already at the end of my presentation. So Azure Quantum is actually not yet available. So Microsoft is, just like IBM, working on a real quantum computer. And it's going to be used for optimization, machine learning, and also to do some quantum simulation on like a cloud level. Microsoft already gives you access to different quantum hardware. So they have their own hardware where they're still working on, so it's not yet finished. They're also partnered with external companies like IonQ and Honeywell, and they are using ion traps kind of quantum computers. They are also partnering with QCI, and they are using superconducting quantum computers. I don't have time to talk about all of these in detail, but tomorrow during the workshop, I will talk about them more in detail. So let's go back to Q#, and we can see that it's 60. So it's around 50 because it's using a pseudo-random generator on your local machine. So it's always going to be around 50%. Of course, a percentage only works when you're actually running your algorithm an infinite amount of times. We're now only running it 100 times. So with that, my time is basically run out. So I hope you have seen a glimpse of quantum computing. I hope you have an idea of why it can help us. Again, you can contact me also after this session. And tomorrow there will be a 2-hour workshop where we are going to actually do some Q# development, and we will do some more examples that are actually meaningful instead of the thing that I just did.